K contained in U. Okay, and yeah, so U is open. U contains M, and F, we take a Lipschitz map from U to Rn plus, to any other Euclidean space. Call it Rp, it can be any other Euclidean space. And this is Lipschitz. And using what we know about C1 submanifolds, we know that the directional derivative that there exists, a set E, contained in Nj with Hn, yes, contained in Ej, that's right, with Hn E equals 0, and all the directional derivatives for every x in Nj minus E, we have that all the directional derivatives exist. This is at the point x. All those directional derivatives exist and are linear in the variable tor, and this is for every tor in the tangent space, classical tangent space of Nj. Linear in tor on this tangent space, it's a linear function. So you see, because of this, then that may, and remember this not only exists, but remember we also pointed out that it's the same just as the ordinary directional derivative in the surrounding Euclidean space. So it's equal to ddt of f x plus t tor, evaluated at tor equal to 0. And you see, that means that really this guy exists without, this doesn't, notice this part of the expression doesn't depend on Nj, right? So of course, the tors depend on Nj, they're in the approximate tangent space, but that's the same as the approximate tangent space of M for almost every x in Mj. So you see, that means that we can now make the same statement because of this. We can now make the same statement about M. So thus, there exists a set E contained in M with Hne equal to 0, set of measures 0 contained in M, such that all of the directional derivatives for every x in M minus E, all the directional derivatives, that is d tor f at x, exist and equal to this same thing, d dt fx plus t times tor, evaluated at t equal to 0. That's true, it exists and is equal to this for every x in M minus E, and for every tor in Txm, and furthermore, this is linear in tor on this approximate tangent space. So that's very, very useful fact. So now we can start doing quite a few of the things that we were doing on C1 submanifolds we can now do on rectifiable sets. So let's talk about a couple of those. So we've got this map here. So in particular, we can define x in m minus the set of measure 0, we can define dfx dm fx, that's the induced linear map. Maps into the same space, txm, and it's defined in the usual way. This is exactly what we did when we were talking about C1 submanifolds. It's defined by dmfx hitting Tor is simply equal to this directional derivative. Notice that is a linear map, that's what we just said. That these not only exist, but they're linear in Tor. So that does give you a linear map. And also a special case is when when p is equal to 1, then f is a real valued function. So special case, p equals 1. So we've got a real valued function, and we can talk about the gradient. For every, again, for as long as we avoid this set of measure 0, for every x in m minus e, we can define gradient fx equals the sum, just as we did in the smooth case, sum I equals 1 up to n, a directional derivative in the direction tor I of f at x times tor I. And here tor 1 up to tor n is an orthonormal basis for the approximate tangent space now. Orthonormal basis for the approximate tangent space. And we can also use the alternative expression that we derived. We can also write that this is also equal to the sum j equals 1 up to n. In fact, let me not bother with that just for a minute because I want to mention something else. So we can do that. And so that's the gradient of a real-valued function. Lipschitz function, as long as it's defined in a neighborhood of the manifold. Notice it is important that f is defined in a neighborhood because this, see this expression here, this x plus t tor is a straight line emanating from x. Now x is in the submanifold, is in the rectifiable set, but this line is not. So it's rather important that we do have f defined in a neighborhood to do this. But of course that's no problem because remember we've got our Lipschitz extension theorem that says that in any case if you've got a Lipschitz function f defined on just on the set M, then you can always extend it to give a Lipschitz function defined on the whole surrounding space. So that's no problem. And similarly, if you take a vector field x equals x1 to xn plus k, where these are Lipschitz, on U, and we can also define the tangential divergence just as we did in the real-valued case. And we can define div sub m of x equals the sum. Now remember how this went. We use the same orthonormal basis, and then we take tor I dotted with the directional derivative of the vector function x, evaluated at the point x. And that makes sense for hn almost every x. And it's tor I again as an orthonormal basis for the tangent space. So we can do all those things. And let's also check now that we can prove the area formula. So there's also an area formula. Just as there was in the C1 case, there's an area formula in the rectifiable case, because you simply, the area formula you see holds on mj. So therefore it holds on mj because for two reasons. One is that mj is a subset of nj, and the other is that the approximate tangent space of mj is the same as the approximate tangent space of nj. So this implies that the area formula holds on mj, and it looks just as it normally does. If you take a subset A contained in mj, then the integral of the Jacobian m f dhn over A, this has to be measurable, of course, hn measurable. This is equal to the integral you count the number of points in the pre-image of A intersect f to the minus 1y. And this is, well, of course, we've got to recall what the conditions are, though, right? This is this is for the case when mapping f, which is here somewhere, or at least it was, seems to have vanished now. Here we are. In the case when p is bigger than n, remember that's when you can use the area formula, when p is bigger than n. So if p bigger than n, the area formula holds. So it's dhn y, and that's for every j. But you see, this is a finite union, so now we just take a sum. So therefore, if you take A contained in M, then you simply apply this to each, then you can write A. Remember, this is the union, j equals 0 to infinity, disjoint union, mj. So we can apply this formula with aj, so you can write A equals the union of aj, disjoint union, where aj is equal to mj intersect A, and simply apply this to each j, and then sum. Using the disjointness of the union, and that gives you the area formula on M now. Jf M dhn equals integral h0 A intersect f to the minus 1y dhn. And of course the Jacobian is the usual Jacobian as it was in the C1 case, except that we use the approximate tangent space. So the jmf at x is equal to the square root of the determinant of d tor I f dotted at x dotted with d tor j f at x. So this looks exactly like the formula for the C1 case, except that we're now using approximate tangent space. So again, tor 1 up to tor n is an orthonormal basis for the approximate tangent space. Okay, so that's what happens when p is bigger than n, and if p is bigger than or equal to n, and if p is less than n, you can use the co-area formula. So similarly, I won't go through that argument again, but again, you simply use this decomposition the way we've done here, and you use the fact that the approximate tangent space of M is the same as the approximate tangent space of Nj for almost every x in Mj, and just use the co-area formula from the C1 case. And so similarly, the co-area formula for p less than n is the integral. You get nice bounds on the k-dimensional measure of A sec f to the minus 1 y dhn y. Integral over dhm, integral over m over p is equal to again the Jacobian fx a dhn let's see, this is the n, right, n is equal to m plus k. Or in other words, k, the k that appears here is equal to n minus m. Oh yeah, actually, that's a notational problem, isn't it? Because I said this is in Rn plus k, so let's reserve k for that formula, so let's make this L. I don't think that k appears anywhere else in this discussion, so it's okay. So that's, again, so everything works out now. We can do all these things that we were doing in C1 submanifolds now on any countably n-rectifiable set, as long as we respect these conditions. The M has to be Hn measurable and locally finite measure. All right, so that's good. So we can do all that, and now we can proceed. So what was one of the other things we did in when we were talking about C1 submanifolds? One of the other things was that we talked about the first variation. So now we can talk about the first variation of in case M is a rectifiable set. So let's do that. Okay, well, that's we have same M, and we take a one-parameter family just as we did so we take phi equals phi, depending on two variables. This is in the interval minus epsilon epsilon, the t variable, and the x variable is in this open set U. So we've got this sticking with the same picture. Here's M, and we assume that we're working in an open set U which contains M. And the conditions are that this should be a map from U back into the same space, back into the same ambient space. So we just agreed, I think, that we're working in the space Rn plus L. Okay, so this is mapping U into Rn plus L. So remember, this is also contained it's an open set in Rn plus L. It's mapping a subset of Rn plus L into Rn plus L. And the usual conditions that phi should start, let's agree to also the usual notation. Let's let phi sub t, the function of x that you get just by freezing the t variable. Like that. And phi sub 0 should be the identity. So this is a one-parameter family of maps, and it starts off with the identity on U. That is, phi sub 0 should be the identity. In other words, phi sub 0 x should be equal to x for every x in U. And the other condition is that it should fix everything outside a compact set. So, so the other condition is that it should exist a compact K contained in U with phi tx equals x for every x in U minus K, and for every t in minus epsilon epsilon in this small time interval. Okay, that's exactly what we did in the smooth case, and now we can proceed as we did in the smooth case. So let's look at the measure of the image of M intersect K under this one parameter family of maps. So we're interested in the first variation of that, rate of change of that. Well, remember, we've got the area formula, which we just, I think I've covered it up here, but it's here somewhere. So we've got the area formula to work with. And in case, remember, this right-hand side here is equal to, in case f is 1 to 1, this is always 1. So this is simply equals Hn of the image, Fa, if f is 1 to 1. So that's just the Hausdorff measure of the image. So that's what we've got here. Notice that for t small enough, this is 1 to 1, of course, because it starts off with the identity. So it's certainly 1 to 1. for small t. And then we get, by the area formula, the image is equal to the integral of the Jacobian over m intersect k. Talking about m intersect k here. So this is Jacobian of phi t, dt, dhm. Now, we compute, so that means that we can proceed exactly as we did in the smooth case. Notice it doesn't matter that m is not smooth, because all we've got here is this Jacobian expression, which is a smooth function of t. So it certainly makes sense to take the derivative. And of course, by the usual theorem, you can take the derivative under the integral sign. Everything is finite here, and everything is smooth as a function of t. So t equals 0. And let's see, how did I say that right? I think I forgot to say what the conditions on this are. Remember, we want to take, we want to look at the first variation. We want to take the initial velocity vector. So x at x is the initial velocity vector of this one parameter family. So we want that to be, I want this to be C1, so that means this had better be C2. So the one parameter family, C2. By the way, notice that the one way to do this is just simply to take phi tx equals x plus t times the vector field x for any given vector field x. That's one way to do this. But in general, whenever you've got a condition like this, then you can do this. And derivative at t equal to 0 is that. And we did the computation for this. We computed this. Remember, this is the same formula. JF is exactly the same formula as in the smooth case. So we can use exactly the same argument that we were using in the smooth case. And we found that this was the same as m intersect k div sub m of x, dhm. So that's the so-called first variation formula. The first variation is exactly the tangential divergence of the initial velocity vector that you get from time 0. Okay, so that's good. So we did all that computation, and that computation doesn't change. It's exactly the identical computation. All right, so we're going to make use of that formula. Oh yeah, now there's one other technicality that I'm not sure I mentioned before, so let me come back to this area formula for a minute. Notice you can get a slightly more general formula if you take any non-negative h mapping from defined on M, Hn measurable function, non-negative on M. And remember, you can always approximate H by an increasing sequence of simple functions, Hn measurable simple functions. So you can find an increase, there exists increasing sequence. Let's call it Cj of simple functions. That means each and non-negative. Simple functions which converge to H pointwise everywhere, with phi jx increasing to hx for every x, no exceptions, for every x in M. You can always do that. And remember, each of these phi j's is a simple function, so it has the form some constant, some I equals 1 up to some number n depending on j, aij, indicator function of ai, Aij, where each Aij is Hn measurable and they're pairwise disjoint. These are pairwise disjoint for each j. So A1j up to ANJJ are pairwise disjoint subsets. So you can always do that for any. And then you get the integral of, so you plug in place of A here, we're going to plug in this guy, the indicator, we're going to plug in that guy in place of A. And yeah, in place of A we plug that in and we multiply by this constant on each side. And use the linearity of each side, right? So you do that, you sum from I equals 1 up to nj, and that tells you that the integral over m of this indicator, of this simple function, Vj, times the Jacobian, Thn, is equal to the integral with respect to h0 of Cj, integral over the pre-image, f to the minus 1y, that's the pre-image of the point y. dh0, so it's just counting measure, and then it's dhny over the target space, which was Rp. Remember, this is the case P bigger than n, or actually bigger than or equal to n. It doesn't have to be strictly bigger. Bigger than or equal to n. So we get that. And now just let j tend to infinity, and you see that gives you the integral of h. So by the monotone convergence theorem, this tells us that we get a nice formula for integration of any function over m. You get the integral of the function h times the Jacobian is the same as integrating over Rp over the pre-image, minus 1y, of h, dh0, dhnY. And remember, this is, after all, just the this is just counting measure, so you can actually write that out explicitly. This is the same as the integral over Rp. It's the y variables are living in Rp. And then this is just the sum of x in the pre-image. dhnY. If there are, yeah, and that, of course, this may be plus infinity at some points, but that's okay. The vague integral can handle that. That's fine. So that's the general area formula. We're going to make use of that in a couple of places. So that's a nice fact, that you just simply use the area formula as we proved it, and then simply approximate a given non-negative measurable function by an increasing sequence of simple functions, non-negative simple functions, and you get this nice general formula. Very useful formula. Okay, so that's our first variation formula, and that's the general area formula. Okay, so now let's see. I think that's all I needed to say about that general stuff. Yeah, so we'll come back to those results in a little while. So now, let me say something about purely unrectifiable sets. So obviously, it's important to understand that not all sets are countably rectifiable. There are sets known as purely unrectifiable sets that are rather nasty and have no nothing like an approximate tangent space at most of their points. So let's talk about purely unrectifiable sets. So the first thing, definition, a set P contained in Rn plus K is purely n unrectifiable if it contains no n rectifiable subset of positive measure. So you look at all the subsets, you'll never find a countably you'll never find a countably n rectifiable subset of positive measure inside this set. And well, one nice fact is that any set, we'll prove this in just a second, if you start off with an arbitrary set of finite measure, finite n-dimensional Hausdorff measure, then you can always decompose that set into a union of a purely unrectifiable bit and a countably n-rectifiable bit, disjoint union. So let's state that. So lemma. Suppose A contained in Rn plus K, and A can be written as a countable union of sets of finite measure. So A doesn't actually have to have finite measure as long as you can write it as long as it's sigma finite. You can write it as a countable union of things of finite measure. H and AJ finite for every J. Then there exists, then you can write, then A can be written as R union P with R countably n-rectifiable and P purely n unrectifiable. In accordance with this definition here. Okay, so this sounds like something, since it's so general, it's probably not very deep, and indeed it's not. I'll give you the proof now. So let's check the proofs. One other part of the conclusion before we do that. If A is Hn measurable, by the way, this is the disjoint union, that's important. If A is Hn measurable, then you can take R to be a Borel set, and there exists a Borel set R satisfying this conclusion. Notice that then P is automatically measurable then too, because P would then be A minus R, so that would be automatic. But you can, the content of that last bit is that you can choose R to be a Borel set if A is Hn measurable. We're going to prove this part first. So assume A is Hn measurable. Let's do that case first. And then, without loss of generality, you can take each of the AJs. Each of these AJs can be taken to be each AJ is Hn measurable. That's clear, isn't it? Because you can always take, I mean, we know that we can always find, remember Hausdorff measure is Borel regular, so we can always find a Borel set B which contains HA with the same measure. So this is Borel. And then, in particular, that's finite by assumption. And then you can write A equals the union Bj intersect A. J equals 1 to infinity. And then each of these is measurable now. Hn measurable. So that's no problem. So no problem. We can assume that each Aj is Hn measurable just by using the Borel regular property of Hausdorff measure. Now we're going to prove that we can decompose like this. So the idea is that you want to split off as much of the Hn, countably Hn rectifiable stuff that you can, in some sense. So we're going to work with these Aj's, which are now measurable. So you let alpha j be the sup, maximum that you can attain by the sup of the set of Hn Bj such that Bj, let's call it B, no need to call it, such that B is countably n rectifiable and B contained in Aj. So forget these B's now. That was just to justify our claim that we could do this. So forget about the B's. Let's concentrate on this now. We're assuming the Aj's are measurable now. So you do that. You take the supremum of measures that you get by taking countably unrectifiable subsets of Aj. Now clearly you can attain that value alpha j, right? Because you can pick a sequence bi with, you can pick a sequence bi contained in Aj with limit Hn bi equals alpha j by definition of sup, right? And then you just take the union of these. The countable union of n rectifiable sets so implies that B equals union Bj Bi. When you take the union, you actually attain this value. And it's still countably n-rectifiable because, as I said, the countable union of countably n-rectifiable sets is again countably n-rectifiable by definition. So certainly we have that. Okay.
Doesn't need to be finite measure.
No, but as long as you can decompose it into sets of finite measure. Of course, that one. Oh, what did I? Where did I do that? Oh, sorry. Yeah, that wouldn't be very good. That would be a very weird. Because n is the Hausdorff dimension that we're talking about. Right. Thanks. So we can certainly attain this value, and now let's call this C, in fact. And it depends on J, so we'd better call it C sub J. So we are going to write, and this, notice this is a Borel set. This is a countable union of Borel sets, and it's countably n-rectifiable. Yeah, so we can certainly do that. So we attain this value. So this becomes, actually this soup is really a max then, right? You can attain the maximum by this process. Okay, so we've got this countably n-rectifiable set which attains the maximum value alpha j. And then the claim is pretty obvious, isn't it? The claim is that aj minus cj is purely unrectifiable, purely n unrectifiable. I know if you haven't seen this before, it's a bit hard to keep track of the numerous definitions, but let me remind you, purely n unrectifiable means simply that you cannot find a countably n-rectifiable subset of positive measure inside the set, right? So that must be true for this, right? Because otherwise, you can find a C1 submanifold. Remember, countably rectifiable, n-rectifiable sets have the property that they intersect, that you can decompose them as a countable union, a set of measure 0 together with subsets of C1 submanifolds. So if they've got positive measure, that means that they certainly intersect some C1 submanifold in positive measure, right? So by definition, so there exists a C1 submanifold n with Hn of n intersect aj minus cj positive. But of course that would be, yeah, okay, I think yeah, I actually want this to be a Borel set. Let's see. Right. Okay. So, right. Now notice this is a measurable set, right? So certainly there's a Borel set contained in it of positive measure. So let's finish the argument here. Hence, there exists a Borel set. Call it B, contained in n intersect aj minus c, which is of course contained in aj minus c. That's the important thing, with positive, which is countably n rectifiable. Of course, it's countably n rectifiable because it's a subset of a C1 submanifold. So that's certainly countably n rectifiable, which with positive measure. But you see, that would be a contradiction, right? Because then this is disjoint from Cj, and B union Cj would then be a Borel subset of Aj, which is still countably rectifiable. This is the union of two countably rectifiable sets, and it's got bigger measure than this number alpha j. So that's a contradiction. So the claim is correct, purely unrectifiable. So that takes care of the case of the theorem. It takes care of this lemma. So we've done this case. Oh, right. Oh, okay. Good. Just got time to finish this. So we've done that case. So now we do the general case. So just pick a Borel set general case. Pick a Borel set B containing A with the same measure. Could be infinite, but that's okay. No, I think I've got to do this with each Aj. So B containing Aj with, call it Bj. Pick a Borel set Bj containing Aj with the same measure. Finite. And then that means that, so we can apply the case that we just proved, this case, which we've already proved, so apply star to the union of the BJs. Then we get j equals 1 to infinity. Then we get union j equals 1 to infinity of bj must be equal to R union P, where this is purely unrectifiable, purely n unrectifiable, and this is countably n rectifiable Borel. But then we're finished because we simply intersect both sides. Notice this contains A, so we get A, take the intersection of each side with A, we get A equals A intersect R union A intersect P. And that's it. This is a subset of a countably n rectifiable set, and therefore it's countably n rectifiable. And A intersect P is the subset of a purely n unrectifiable set. So that's also okay. All right, let's take a break for a few minutes. Now let's see. Okay, so yeah, so let's talk a little bit more before we go on about purely unrectifiable sets. So there's a nice criterion that enables you to check whether or not a set is purely unrectifiable or not. So there's a nice lemma. Suppose S is contained in Rn plus K. And let's introduce the following notation. For J1 bigger than or equal to 1 less than J2 less than Jn less than or equal to n, we're going to let P J1 up to Jn be the orthogonal projection of Rn plus K, that's the whole space, onto the subspace, the n-dimensional subspace that you get by using the standard basis vectors, ej1 up to ejn. So onto the span of ej1 up to ejn. So ej are the standard basis vectors with zeros everywhere except in the j slot where there's a 1. And suppose oh yes, thank you. Yeah, otherwise it wouldn't be very wouldn't be very difficult to choose the j's. Right. Sorry. And suppose that. The following is true. Namely, when you use this projection, when you project onto this span, you project this set S onto this span. Suppose you get a null set. It's always 0 for every choice of J1 up to Jn. Then S must be purely unrectifiable. It's purely unrectifiable. So this is a convenient quote. Notice it's only a sufficient condition to get unrectifiable. I'm not claiming that it may happen that S is purely unrectifiable and still projects in a non-null set in some directions. It can happen. I'll say a bit more about that in a minute. But if you have a set that projects null in every one of these directions, then indeed it must be purely unrectifiable. So the proof is easy, of course. It's not, I guess you can guess because of the nature of the theorem that it's not going to be difficult. So, right. Well, difficult enough that I can't remember the proof, however. Okay. Yes. Okay. Suppose on the contrary, it's a proof by contradiction. Suppose on the contrary that S is not purely n unrectifiable. Now let's remind ourselves what that means. That means that there must be a countably n rectifiable subset of S with positive measure, right? So suppose there exists a countably n rectifiable subset A contained in S with positive measure. Now remember, that means that A can be decomposed as a countable union where the first, say m equals 0 to infinity. mj, from j equals 0 to infinity. So where M0 is a null set and Mj is a subset of a C1 submanifold, right? So that means then there must be at least one. Then there exists a C1 submanifold, an n-dimensional C1 submanifold, N, with HNA intersect N positive. It's just using that decomposition theorem for countably n rectifiable sets. Now, if that's the case, then the claim is that there exists some point x in A intersect N with Hn A intersect N intersect B rho x positive for every row positive. Stare at that for a minute. This is a general property of sets of positive measure. If a set's got positive measure, then there must be at least one point in the set where it intersects a ball of radius rho as a positive in a set of positive measure, and that must be true for every row bigger than 0. And that's pretty easy to see, because otherwise for every x you would have, here's A intersect N, otherwise for every x in the set you'd have some radius rho x where the measure is 0, right? But then you see you can find a countable covering of such things. Notice you can certainly take a countable covering. You can use the 5 times covering lemma for that, because the balls of radius rho over 5, rho x over 5, can be made disjoint. You can pick a collection of balls of radius rho x over 5, which are disjoint, and that's a countable collection. Any collection of disjoint balls in Rn, of course, has to be countable. And then you just enlarge them up to the original radius, rho xj, and you'll cover the whole thing by balls, each of which intersects A intersect N in a null set. That would contradict this statement. So this is certainly correct. You should check that for yourself if I went a bit fast there. But it's clear that you can do that. So there's some point, at least one point, where every ball intersects the thing in a set of positive measure. Now, think back about our discussion of C1 submanifolds. This point x is, of course, in N, C1 submanifold. Remember when we were discussing local coordinate representations, we said that you can always find J1 up to Jn such that the projection onto the Rn downstairs gives you a local coordinate representation, the inverse of a local coordinate representation. So there exists, so recall from our discussion of local coordinate representations, recall there exists a row big, as long as you take row small enough, you can do this locally, right? It's a local coordinate representation, but well, that's fine. We've got this is true for every row, so we can take row as small as we like. So recall that there exists row bigger than 0, such that, and there exists, and there also, most importantly, there exists some choice of these numbers, J1. There exists row bigger than 0 and J1 up to Jn with Pj1 up to Jn restricted to n, a local restricted to 0 x intersect open ball. That is a local C1 diffeomorphism, is a C1 diffeomorphism onto an open subset contained in Rn. It's contained in the span of these things, actually. Contained in the span Ej1 up to Ejn. Okay, so certainly no problem with that from our discussion of local coordinate representations, we can certainly do that. But then you see this is the inverse of this is Lipschitz. The inverse of this map is a C1 map, hence locally Lipschitz. So the inverse, which is the local coordinate representation for this part of N, the inverse is locally Lipschitz. In fact, it's C1. C1 maps are always locally Lipschitz. So it's locally Lipschitz, but then it takes sets of measure 0 to sets of measure 0. Sets of Hn measure 0. 2 sets of measure 0. But that's a contradiction because it takes that set is positive measure. So that's clear. So that's it. So that's proved. So let me give one example of how this is used. We'll construct a purely unrectifiable set. Okay, I'll probably get this wrong. We've actually got to construct a set here. We actually need to do some arithmetic. So we've got 0, this is the unit square in R2. So this is the x-axis, and this is the y-axis. So you start with the unit square. You've probably seen this before or something like it anyway. And you take these 4 squares of edge length 1/4 at the corners. So this is 1/4. So that means this middle thing is 1/2. Because the whole edge has got length 1. Now notice that if you project, so let's have a look at these lines, that these lines of slope minus 1/2 that goes through here. So far, so good. Things sort of look parallel. And let's do another one here. This, another one here. Now look at the line of, these are lines of slope minus 1/2. Look at the line. Look at the y equals 2x line. That's slope 2. That's orthogonal to these. So let's look at the projection onto that. So this is y equals 2x plus a constant, because it's not passing through the origin, but it's got slope 2. Now, I didn't do that too well, did I? You've got to forgive me for my bad geometry, but that's supposed to be a right angle there. Okay, so that means that this is, let's see, now observe that these 4 sub-squares project fully onto this line. For instance, this one here projects onto that segment. Projects onto that segment. This one here projects onto that segment. This one here, this one, projects onto that segment. And this last one projects onto that segment. So these 4 squares still project fully onto that line segment. Let's do some arithmetic. We want to know the length of that line segment. It's probably a bit hard for me. Let's see. I know what the answer is, but how does one check that? Let's see. It's yeah. Well, it's not so important. You can work it out for yourself. The length of that segment, sigma, that's the yellow thing, has length 3 over root 5. Which I believe is approximately 1.31 or something like that. So that's the first point. These 4 little squares project fully. Now think about that. That means that if you do this again, then we've got 16 little squares now instead of 4 little squares. We forget the original 4, we just take the new ones. So the new squares have got length 1/16, edge length 1/16, and there are 16 of them. Now notice they still project fully onto the yellow line segment because they project fully onto these 4 by the same argument that we just gave, project fully onto this bit, you see? And these 4 project fully onto that bit, and these 4 project fully onto that bit by the same argument that we just gave. So always, no matter how many times we iterate this procedure, they always project fully onto this line segment, sigma j. All right, so that's good. Now, so we do this. So we iterate this. So at the nth step, we have 4 to the n small squares of each of edge length 1 over 4 to the n. One over 4 to the n. And of course we call that Cn. It's the union of 4 to the n squares, each of length 1 over 4 to the n. And notice, of course, trivially, Cn plus 1 is a decreasing sequence. Cn plus 1 is contained in Cn for every n. And furthermore, that means that the intersection is non-empty because it's a decreasing sequence of compact sets. So the intersection, let C be the intersection. N equals 1 to infinity. That's non-empty compact set. Now I claim it still projects fully. Onto y equals 2x. That's a constant. Now that's not going to always be true if you do this process randomly, but whenever you have decreasing sequence of compact sets, it will be true. Because think about it, if you take a point x here, anywhere on this line segment, there's always, so x in the segment sigma implies that for every n there exists an xn which projects to it. So let's call the projection P. Projection parallel to the y equals minus a half x lines. So there exists an xn with dxn equals x. But you see then that by compactness there's a subsequence xnj converging to x in C. And of course, just take limits here, converging to y, and that means that py is equal to x. Okay, so it still projects fully. The limiting compact set still projects fully onto the line segment sigma. So it's certainly got positive. So hence, H1, the one-dimensional Hausdorff measure of C, well remember, that's bigger than or equal to the one-dimensional Hausdorff measure of the projection, because the projection, this is the projection onto the line segment sigma, that's an orthogonal projection, that's got a Lipschitz constant 1, right? So this is less than lip p to the n, but lip p is equal to 1, so bigger than or equal to that, and this is greater than or equal, in fact equal to if you believe me, 3 over root 5. Really annoyed I forgot how to compute this 3 over root 5. I think you take this down to here. And that's a half there, right? That's 1, and you take this triangle. Yeah, that's the way to do it. And then call this sigma. This is sigma over 2. So by Pythagoras' theorem, sigma squared plus sigma squared over 4 equals 3 halves squared, which is 9 over 4. So that's it. You work that out, you'll find it's 3 over root 5. Okay, so that means that this has got positive measure, a positive one-dimensional Hausdorff measure. But there's also an upper bound, H1 delta of C. You see, we've got a ready-made covering. You don't even have to cook one up. It's already there. The covering is Cn, right? And that's the diameter of each of these squares is 1 over 4 to the n times square root of 2, right? So H delta C is less than or equal to 4 to the n times 1 over 4 to the n times square root of 2, using the definition of H1 delta, which is root 2. And that's actually 1.41 approximately. That's pretty amazing, actually. So that means that H1C is less than or equal to root 2, which is approximately 1.41. That's pretty close. This is approximately 1.31, I think, or something. Anyone got their iPhone here? You could check that. So there's only a small difference there, but anyway, they're correct upper and lower bounds. By the way, this one's only true as long as this is less than delta. But you see, that's eventually true for just take n large enough. So that's true for every delta. So just take the limit of delta and you get this. H1C less than or equal to square root of 2. Okay, that's good. And but now, where does this lemma come into play? Well, you see, think about projecting onto the x-axis. How many, if we project Cn onto the x-axis, how many squares of how many intervals of length 1 over 4 to the n do we get? We only get 2 to the n, you see, because they overlap. The projections over, you see, there's a huge overlap here. Project so that, so the projection, so let P be the projection onto the x-axis. Orthogonal projection onto the x-axis. And if you take the orthogonal projection of Cn, that's actually 2 to the n intervals of length 1 over 4 to the n. So the total length, H1, total length, the one-dimensional Lebesgue measure of that, is just 2 to the n over 4 to the n, a half to the n, in other words, which tends to 0. But this is a decreasing sequence of sets, so this implies that the L1 of PC is equal to 0. So it does null project onto the x-axis, and similarly it null projects onto the y-axis by the same argument. Similarly, L1 of projection, orthogonal projection onto the y-axis is equal to 0. So by this lemma, C is purely one unrectifiable. So the lemma implies C is purely one unrectifiable. Yeah, so that's good. That's an example of how to use that theorem. Now that's almost as much as we need. We're not going to spend any time talking about purely unrectifiable sets, but I thought I should at least mention some of these things. The other important thing is the Federer structure theorem. That's really an amazing theorem that gives you lots of insight into what purely unrectifiable sets look like. So the Besakovich-Federer structure theorem. That says, well, let me do the codimension 1 case first, since it's easier to explain. So S, purely N unrectifiable in Rn plus 1. I'll mention the general case in just a minute, but this case is easier to explain. And consider, take orthogonal projections. So for any unit vector, let P eta equals orthogonal projection onto eta per. So this is for any, in other words, eta in Sn minus 1, the unit sphere, to any direction. Take any direction and let P sub eta be the orthogonal projection onto eta per. That's an n minus 1 dimensional subspace, n dimensional subspace. So pictures like this. Here's eta. S is here somewhere. Here's eta. You take the orthogonal projection, eta per. The orthogonal projection to eta. Then the Besakovich-Federer theorem in this case, when we're in Rn plus 1, says that the n-dimensional Hausdorff measure of P eta S is equal to 0 for Hn minus 1 almost every eta in Sn minus 1. For almost every direction, in other words. For almost every direction it projects as a null set. Now think about the retina of your eyes as being the plane we're projecting onto, right? Then that says that this set's invisible if you're looking at it in this direction. It's really extremely weird thing, right? It's invisible from almost all directions. You wouldn't know it was there. In fact, there's some comical things about purely unrectifiable sets. As Brian White once told me this, that you can cook up purely unrectifiable sets which have the property that if you put them out in the garden, then the sun projects down and the shadow will give you the exact correct time of day at every instant of the day. Of course, don't try to construct that object. It's a little bit difficult because it's immensely complex, of course, but you could presumably construct an approximation of that object that gives you at least the correct hour of the day or something, right? Okay, so anyway, so that's the result, and you don't have to be in Rn plus 1, in Rn plus k, and you take any orthogonal projection. Then you look at all the orthogonal projections of n plus k dimensions down onto an n-dimensional subspace. Then the same thing is true. And then this would be the Haar measure of the for sigma almost every p in O n plus k n. This is the Haar measure, which is the natural measure for the. So again, it says that the thing's invisible from most directions. Really amazing. Anyway, that's I wanted to mention that. We don't need that in our later discussion, but it's certainly a great theorem. And let me, by the way, if you're really brave, you might want to look at Federer's proof in his book, but there's a much easier proof now. Brian White, so if you want to look this up, there's a proof due to Brian White where he, an inductive argument, he reduces the n-dimensional case. Besekovich did the one-dimensional case, which is highly non-trivial, by the way. Besekovich did the one-dimensional case. Brian White showed that you can reduce the n-dimensional case to the one-dimensional case. That's, well, you'll find a reference in the latest revision of the text. The reference, 1998. N-dimensional case reduced down to the one-dimensional. A much simpler argument. And then for Besekovich's work, you could read either his original papers, but there's a nice little book by Falconer. Again, you'll find a reference for this in the text now. Falconer's text discusses the case n equals 1. A really nice little book, Cambridge University Press book that does it. Okay, so that's I think that's as much as we need to say about rectifiable, purely unrectifiable sets. Yeah.
So there should be nothing special about orthogonal projection.
Oh well, yeah, okay. Presumably, yeah, but there is something special about orthogonal projection. But I'm not saying that other kinds of projections, but would also give weird results, undoubtedly. But exactly what remains to be seen. Yeah.
I try to understand the stemming. It's some kind of functorial way.
Well, okay. Well, that's beyond me. I don't. As soon as you say functor, I'm immediately lost. Right. Okay, so I think that's as much as we need to say about purely unrectifiable things, but it's certainly a fascinating, really some amazing results that you wouldn't necessarily intuitively expect. Okay, so let's now start talking about, I want to move on to chapter 4 now, which is Introduction to Rectifiable Varifolds. So a definition, well, you take M to be purely, M countably n-rectifiable. Countably n-rectifiable, and the usual assumptions, Hn measurable. And take a positive theta, Hn measurable function theta, on M, real valued. So it's defined on M and it's got positive values. It's a positive function. With Hn M, with locally integrable, in other words, integral M intersect K theta dHn, finite for every compact K. You shouldn't worry too much about this. Theta is going to be called a density function. You should definitely think of it as being positive integer valued. That's by far the most important case, right? So you should think of it as being positive integer valued, but abstractly there's no particular reason for the moment for doing that. So that's certainly the case to think of, so you should keep that case in mind. And then you look at the equivalence class. You take another pair, m tilde, theta tilde, you say that that's equivalent to this original pair means that, well, it means that M and M tilde agree HN almost everywhere, right? So it means that HN of M tilde minus M union M minus M tilde is equal to 0, and also theta equals theta tilde almost everywhere. And theta equals theta tilde HN almost everywhere on the common domain M intersect M tilde. So there's an equivalence relation there. And the rectifiable varifold is just the equivalence class of M theta. So V M theta, the equivalence class, relative to this equivalence relation, the equivalence class. So you can think of it as the set of all M tilde theta tilde with this. And we sometimes label that capital V. Now that's not the final word about how to define varifolds. This is just a working definition for rectifiable varifolds. Things like this are called rectifiable varifold. V said to be rectifiable varifold. There's a much more general notion of varifold that you'll find discussed in the last chapter of the text. We probably won't have time to discuss any of that, but I don't think I wanted to erase that. That's too bad. But that's okay. All right, so that's the notion. Now, there's a bit of notation here, so before we get to anything interesting. So, first of all, there's a measure. Mu sub V is the measure that you get by integrating with respect to theta over a given set. So mu sub VA equals integral over A of theta dHn. So that's that. And there's also the notion of the mass of V. That's just the total measure. In other words, that's integral over all of M. This is for this is A intersect M. And this is over all of M, theta dHn, that's total mass. Piece of jargon. And I think that's that. Now, but we also need to talk about the idea of mapping varifolds. Oh, one other bit of notation. If A is HN measurable, you can talk about V restricted to A. That's just the varifold that you get by taking the equivalence class of M intersect A theta. So, okay, now we also need to talk about mapping varifolds. So suppose that we've got an open set. This is again in Rn plus K, and containing M. And suppose that we've got a mapping F going from U into Rp, where P is bigger than or equal to N. And this should be at least Lipschitz. And let's first look at the case when F is 1, 1. The question is, how should we define what it means to take the push forward of the varifold? If V is this guy here, it's got the countably rectifiable set and the multiplicity function. Well, that seems pretty clear how we should define that. We should just define it to be the varifold that you get by taking the image of the set M, and it should have the same multiplicity that you got from the original domain. So that means, if you think about it, that the multiplicity function would be theta composite f to the minus 1, right? Now that, at first sight, looks like a sensible definition. However, we've forgotten something. One of the hypotheses that we must check before we make any sense out of things like this is this thing. So we've got to make sure that's true. Now, notice that need not necessarily be the case, so let's check. What condition do we need for this condition? So take K compact contained in U, and let's look at this guy. So Fm intersect K. What is that? Well, that's F of M intersect the pre-image of K. K needn't intersect Fm, but that's still a correct identity, nevertheless. Right? If K doesn't intersect M, then this is empty and this is empty. So if K doesn't intersect Fm, sorry, then they're both empty. So it makes sense. So that's that. And then we want to check this condition. So we want to check that integral. So we're going to check this condition, but we're doing it for this variable. So we want to check Fm intersect K. See, there it is there. And instead of M, we've got Fm intersect K. And instead of theta, we've got theta composite f to the minus 1. Dhn. Well, that's equal to f by this identity. That's equal to Fm intersect f to the minus 1k. Theta composite f to the minus 1 Dhn. Now, unfortunately, I just erased where I'm writing now is the formula I wanted to use. I just erased the area formula, the general area formula. You remember the general area formula that we derived earlier using approximation by step functions, by simple functions, it tells us what this is. It would be integral of the Jacobian of f over m intersect f to the minus 1k, and would be theta Dhn. This is the general area formula that we derived earlier today. It's the general area formula with theta in place of h. That function h we were talking about, the general area formula. And you see there's a problem. K is compact, but f to the minus 1k need not be compact. So that doesn't work in general. That's wrong. Unless you assume f is proper, meaning the pre-image, so that we have to assume that. So this is Lipschitz and proper. That means that K compact implies f to the minus 1k compact. For instance, that's trivially okay if f is the identity map. It's not okay if f is a constant map, of course. That wouldn't work. But so various situations where you can check that. But we really need that. So this is then okay. This is then finite measure and we're integrating, so that's fine. So that's okay, makes sense. So that takes care of case 1. This is our definition in case 1 of f is 1 to 1. Now this, we just use the area formula. That gives us the hint about how to proceed in the general case now. In the general case, well, let's talk about that. What should the definition be? Think about having a curve. This is the case n equals 1. So m is, say, just a curve, and f is a mapping. Lipschitz map, proper Lipschitz map, or a Lipschitz map in general. Suppose that f, it's no longer 1 to 1 though, so f might do this. It might take the curve and make it double around here and then come back and stick to itself for a while. That would be one possibility. If you've no longer got a one-to-one map, then that sort of thing can of course happen. Now if that happens, you obviously should really think of the image here as having multiplicity 2 there, right? That's a natural, that seems sensible, that you should count the multiplicities. That way you won't lose any length either, by the way, because if we take the length, we'll account for all the length, depending on how, so I'm sort of not losing mass. Any mass that we get over here is accounted for by the Jacobian of f. Nothing else would be involved because we've counted multiplicities correctly. Now that's what the area formula does. The general area formula, if f is not 1-to-1, this, remember what this looks like? It's the integral dh0 of it over f to the minus 1 dh0. It's a counting measure of the pre-image dhn. Oh, we still, yeah, that's right. So that would again give us theta jf, but instead of, it's, yeah, that's right. So that's, right, so, yes. So instead of this guy, we would have, if we want to keep track of the measure, we should take theta tilde, where theta tilde, so our definition should be, instead of that, so this is case 2, f merely proper, and no longer 1-1, then the correct definition, if we want to take care of those sort of things, is that we should define this to be, again, the verifold with the image, but now the multiplicity should be integral of sum x in f to the minus 1 y of theta x. So this would be, let me write that slightly differently. So this should be theta tilde, where now theta tilde is equal to the theta tilde at a point y is equal to the sum x in f to the minus 1y of theta x. Now that's exactly the thing that appears in the area formula, and again you'll get this expression. So, but this time with theta tilde here. So you'll get, oh sorry, with theta, no, this is still theta, this guy. So you'll get, so the area formula now, yeah, let's check that. So let's check, that make sure, let's do the check again to make sure that we've got something sensible if we make this definition. So we've got to take the, again, integral fm intersect k, theta tilde, where theta tilde is defined in this way. Okay, we've got to check that makes sense, finite. So that's, as before, that's the same as fm intersect f to the minus 1k, theta tilde, dhn, and but that's exactly the thing that appears in the area formula. That by the area formula, the general area formula, this is exactly the same as integral over m intersect f to the minus 1k of the original theta times the Jacobian of f dhn. And that is indeed finite as long as f is proper. So indeed, this seems to be right because it seems to work correctly with these sort of intuitive examples. It seems to keep track of the multiplicity in the correct way, and it also has the property that it does indeed give you this nice formula. So either way, regardless of whether f is 1-to-1 or not, as long as it's proper, you get this expression for the integral of theta tilde over the image. In other words, for the measure of the image variable, for the measure of this guy, you get this nice formula with the original theta times JF. So we'll continue that discussion next time.